So notice here how the covariance is really equal to a correlation times these two other things. Or more precisely, the covariance is equal to the correlation between two variables multiplied by the standard deviation of each variable. Well, what if we put both x and y in z-score form? If you're familiar with z-scores, you may recall that a z-score has a mean of 0 and, most importantly for this, a standard deviation of 1. We can put any variable in z-score form, and if we do that, we'll get a mean of 0 and a standard deviation of 1. So in z-score form, here's our basic covariance formula. Recall that standard deviation is 1 for both x and y in z-score form. So if that's the case, then the covariance is equal to the correlation times 1 times 1. Or, as we saw before, these will just drop off. So in z-score form, the covariance is equal to the correlation. So therefore, when both variables are in z-score form, the covariance equals the correlation. So you can see how closely related these two measures are. As we saw before, the covariance is just equal to the correlation times the standard deviation of each variable. Therefore, like correlation, covariance is really just a measure of the relationship between two variables. Unlike correlation, however, it's not scale-free, but instead it's scaled by the standard deviation of each variable. And we saw that when we multiplied the correlation times the standard deviation of each variable to get the covariance. But putting the variables in z-score form, or making them scale-free in other words, shows that the covariance is very similar to correlation. As I said before, it's really just the correlation multiplied by the standard deviation of each variable. So for example, if we had the following, the correlation of 0.5, standard deviation of x of 10, and a standard deviation of y of 5, then using our formula, we would find that the covariance is equal to 0.5, the correlation, times 10, the standard deviation of x, times 5, the standard deviation of y, or the covariance in this example is equal to 25. Now, if we put these variables in z-score form, they aren't here, but if we went ahead and did that, what would the covariance be equal to? Think about that for a second. If these were in z-score form, their standard deviations would be 1, right? Each would be 1. So what would the correlation be equal to? It would be equal to 0.5, wouldn't it? It'd just be equal to the correlation between x and y, because these two terms would drop off. Now, one last note. When I say we put it in z-score form, that doesn't do anything to change the variable in the sense of corrupting the values or negatively impacting them. For example, if we had exam scores and you scored the highest on the exam and your friend scored the second highest, if we put all the exam scores for the entire class, for example, in z-score form, you would still have the highest z-score or the highest score. Your friend would have the second highest z-score, and so on. So it doesn't change the values in any negative way. All the values retain their same location relative to each other. It just makes them scale-free. So they're on that z-score scale instead of on a scale like 0 to 100% or what have you. So when I say in this video put in z-score form, all that means is we're converting the variables to have a mean of 0 and a standard deviation of 1. But it doesn't change or distort them negatively in any way. Okay, that's it. Thanks for watching.